Greetings. In graph theory, when one has a Hamiltonian graph G, it means that this graph contains a Hamiltonian cycle. But let's first describe what is a Hamiltonian, what this Hamiltonian means in the first place. So first of all, one should know what a Hamiltonian path is. So basically, path, as we know, it's a walk, it's a subset of possible walks on a graph. A walk being you transcend, you go across vertices one by one, across the possible edges, you walk along the graph vertex by vertex. And a path is one where you cannot go to the same vertex twice. We don't return to the same vertex eventually. You always go to a vertex you've not gone yet. So that's a path. But a Hamiltonian path is one that transcends that goes to all the vertices that are in that graph. It basically travels across every single vertex of that graph. It visits every single vertex of the graph, and it doesn't have to visit any of them twice to do so. So Hamiltonian path is basically a path across the graph where it visits all the vertices of this graph exactly once. And a Hamiltonian cycle is the same thing. It's like a path like that again, but it ends in the same vertex, so it goes in a cycle. So you can find a cycle path around the graph such that you go to all the vertices and you don't have to repeat any of them more than once, and you get to visit each of them exactly once. So that's that. And an example of that could be any simple graph, for example, a cycle graph like this. So let's say 5 vertex cycle graph, very simple example. Of course, it's possible for us to visit every single vertex once without visiting any of them twice. We go one by one along the edges that are in this cycle structure. And even if we have some extra edges through, doesn't change the fact. It's still the same point. Nothing's changing about the possibility. The possibility is there. So there's that. And with this, we can directly continue to the idea of the Dirac's theorem. So Dirac's theorem is one that concerns the question whether if graph has a Hamiltonian cycle or it doesn't. So I've described what a Hamiltonian cycle is. And before we get there, let's do one more example. We can, for example, also look at this. So a graph that looks like this. Does it have a Hamiltonian cycle? It doesn't, but it has a Hamiltonian path, right? We can find a way to go to all vertices one by one without repeating any of them twice. We can go this. We visit all the vertices, a Hamiltonian path, but not a Hamiltonian cycle because we cannot return to the same vertex again. We would basically, if we started here, we go like this, and then we have to go to this one, but from this one we must return. And if we start at this one, we will return over this one again. So that's a problem. So there's not a Hamiltonian cycle. And a graph that has a Hamiltonian cycle, that means you can visit all the vertices of it by a cycle, to visit all of them exactly once, only by one cycle, then that's called a Hamiltonian graph. So a graph is called Hamiltonian when there's a Hamiltonian cycle. And Dirac's theorem concerns exactly this. So Dirac's theorem says basically, let's have a graph of vertex set V and edge set E. So this graph now has some properties. Let's say that the amount of vertices, the vertex set, as the magnitude of the vertex set is the amount of vertices that the graph has, is n. And there's one condition first before we move on. That is, n must be at least 3. So example could be, we could think of a graph that will eventually fulfill this theorem, but you don't know what the theorem is yet, but I can say n must be at least 3, a triangle, a cycle graph triangle, for example. But anyway, the point is here, this. If you have a simple connected graph, right? So connected and simple graph, and the amount of vertices of it is 3 and higher, and one more condition is satisfied, then it will have a Hamiltonian cycle. It will be Hamiltonian, because a Hamiltonian graph is when it has a Hamiltonian cycle, as I was said before. So the last condition is if the degree of vertex V, like lowercase v, is higher or equal to 1/2 of n, where n is the amount of vertices, the magnitude of the vertex set, for every vertex v in the vertex set. So if all the vertices have at least half the amount of connected edges as there is in total vertices of this whole graph, then it will be Hamiltonian, as long as it's simple connected like this. So now that we have the theorem, let's look at the graph, an example that doesn't have a Hamiltonian cycle, but we can look and discuss the different adjustments that can be made to make it so. So basically, let's say we can have this one. It has this base structure like a cycle graph 4, and then it has this extra one, and it doesn't have a Hamiltonian cycle because you cannot make one. You cannot think of any. Really, it has a low enough amount of vertices, a number of vertices to be able to look at the different individual options, and from just testing them one by one, one could see. Well, in any case, let's see what we could do. The requirement is as follows: it must have at least 3 vertices, which is satisfied, but the part that doesn't get satisfied, and if we satisfy it, this theorem tells us that we are absolutely guaranteed that there will be a Hamiltonian cycle, and so the graph will be called Hamiltonian, is if we make sure that all the vertices have at least half the number of edges connected to them as there is vertices in this whole graph in total. So the whole graph has 5 vertices. Now half of that is 2.5, but to be sure, we should take the 3. As the minimum, as the 1/2 of the number of vertices. So let's say 3, and with that we will basically want to remake this graph, for example, in a way such that all the vertices have at least 3 edges. So we can just draw new edges, and let's see if we actually need to make sure for all the vertices, if just one added edge could fix it, and namely I could just add one edge here, and it doesn't even fulfill this requirement to be for a guaranteed satisfaction of the theorem. But still, already now we see we can have a cycle that basically takes care of all the vertices, and we didn't have to even make sure to have 3 edges connected to each vertex. Now we could make sure that happens. We could attach one more edge here. We could just make sure that all the vertices have 3 edges connected to them. So this one already has 3 edges, but this one does not, and this one didn't. So now this one has 3, this one has 3, this one has 4 even, this one has 3, this one has 3. So now all have 3, and now with this one, without even looking at it and actually seeing that we can just see a cycle right here, ignoring the inner edges, we could already have a Hamiltonian cycle inside the graph. Now it is guaranteed, because now all the vertices have 3 edges, and that's more than half the number of the elements in the vertex side of the graph.